First up is Lagrangian mechanics. In here you can start from any coordinate system, any system that you find useful. It doesn't need to be Cartesian coordinates, and we call these generalized coordinates. Qi, and then we have of course also their temporal derivatives, again denoted by a dot. And now we introduce an object which is called the Lagrangian, and it is the difference between the kinetic energy and the potential energy expressed in terms of these coordinates. I denote it as a curly L so that we do not confuse it with angular momentum. I'm going to show you an example and everything will be very clear once I do, but this is just a definition at the moment. Now the kinetic energy, you can start out by expressing it in terms of Cartesian coordinates, and then you simply transform it to these coordinates. And this is really the idea. And Newton's equations of motion are then replaced by the following very general equations of motion, where we here have a partial derivative with respect to one of these positions entering this Lagrangian. And here we have a partial derivative with respect to the generalized coordinate itself. And we simply do this one equation each for each of these coordinates. So let us first see how this actually reduces to Newtonian mechanics. So let's just look at a point particle of mass m and velocity x dot. And now this would be the expression of the kinetic energy. And then we have some potential energy, V of x. So our Lagrangian would be simply mx dot squared divided by 2 minus V of x. And then the equation of motion first involves the partial derivative of this term with respect to x dot. So this gives us mx dot. And this partial derivative here simply gives us minus dv dx. And so this is indeed the change of the momentum over time, and this is the force as we normally define it from a potential. And now what is beautiful is that this really works for any kind of coordinate system. So for example, for a system with a central potential, when we want to work in polar coordinates. Let's have a look at this. In there we start from a kinetic energy in 2 dimensions. And given by the formulas above, this can be written in the following way. And the potential energy would just be a function of this radial distance. So the Lagrangian would simply take the form m over 2 times these derivatives here. Minus this potential energy. Now notice that this Lagrangian does not depend on phi. And any generalized coordinate for which this applies we call a cyclic coordinate. And this directly leads to a conservation law, because then we recognize that the derivative of the Lagrangian with respect to phi dot simply has to be a constant. This is a temporal derivative, so this expression here needs to be a constant over time. And now if we work this out, just from here we find that this is actually just the angular momentum. And secondly, when we now look at the equation for the radial distance, then we have to evaluate the following equation. Now on the left hand side, this simply gives us r double dot. So first we get r dot, and then we take another derivative with respect to time. And on the other side, we actually now get two terms. One arising from the potential energy, which we can just write as its derivative again, and another term arising from here. And this takes exactly the form of the fictitious force that we encountered before. So we automatically get this for free. So we get two things at the same time, a much quicker way to derive the equations of motion, and a very general principle that tells us when we get constants of motion, namely whenever one of the generalized coordinates does not enter the Lagrangian. Now this is a really useful way for calculations, and for instance engineers use this all the time. This is a central part of most engineering undergraduate degrees. This is a central part of many undergraduate engineering degrees, at least when I was a student and my friends were doing it. But it becomes even more fascinating. These Lagrangian equations of motion can be derived from a very general principle, which will reappear in some form in quantum mechanics as well. And this is the so-called Hamilton's principle of least action. This is conceptually quite interesting. In there you say that you start from some position in your coordinate space, in this space of generalized coordinates. And this is already a vector. This I here is not an index in terms of enumerating lots of entries, but it's standing for initial condition. So this is my initial condition. So we start at a certain point here, and we want to get after some time to a certain final condition. And in this potentially very high dimensional space, this will be a certain curve that brings us from one point to the other. And now we could pretend that we don't know which curve this is and evaluate a certain number for any possible curve in this space. This number is called the action, and it's simply defined as an integral over time of the Lagrangian, where we just take all these positions and their derivatives as a function of time, and there might be a time dependence in it itself. And of course we are integrating over a particular time, so let's call this t prime. So there is some path q depending on this time, and at this point we end up at our final time, the time that we are really interested in. So this object is called the action. And now we can consider many different paths which are just deviating from this a little bit. So let's say we consider our path with a little addition, which I just call delta q. Just a little sort of difference between these two different paths here. So this would be just delta q. And now you can evaluate the derivative. I know it sounds very complicated, but for any pair of these paths you can calculate the derivative, and then you find that this vanishes exactly when you chose a path which is the path that the particle is actually traveling by. So this is 0 exactly when you fulfill the equations of motion. Now this path here was completely arbitrary, and this one here still looks a little bit as it depends on which path we have taken. So there is also a more general mathematical symbol for this. One just calls this the variation of this action with respect to any kind of path, and this is supposed to vanish. So this is known as Hamilton's principle of least action. It's called the principle of least action because in many cases you find that this particular path will actually minimize the action. So amongst all the possible paths that go from here to here, this is really the one for which this number is the smallest, but it doesn't need to be the case. But in many cases it is indeed true. This can sound quite complicated, but it is a very useful concept, and you might have encountered it in other contexts. it also applies, for instance, to ray optics. So if you have a dielectric medium which can change from position to position, and you ask about the path an optical ray would be taking through it, say including diffraction, from this point to this point here, you can introduce a so-called optical path length, which is an integral over this path, simply parameterized by some parameter s. And now it happens that the paths which minimize this optical length are the paths prescribed by ray optics. And now this is clearly relevant because rays are a simplified description of waves. And in quantum mechanics we deal with waves, while in classical mechanics we talk about particles. But now to see how this relation comes about, we need to go 2 further steps. And the first step will already put us very close to quantum mechanics.